Hello everyone, my name is Komasinyolo. Welcome to another video by Attention Matrix, where we try to make learning fun and easy. Please comment, like, and subscribe if you would like us to continue making this content and you enjoy it or find it helpful. Now on to the next video. Let's get right into it. Okay, welcome to part 3 of our lessons on exponential functions. We did a part 1, the first video of these lessons on exponential functions, where we explained the general form of the exponential function and how to use it and the important characteristics of that general form. Part 2, we focused on a variation of the general form, and part 3, we're going to be continuing on looking at the variation or different other variations of the exponential general form. Okay, so just to recap, the original form, okay, the original form or the original standard equation is as follows. We've got y is equal to a to the power of x. Okay, this is what I call the original form. And in the previous video, we looked at a variation. Variation 1 is what I'm going to call it. We looked at variation 1, or rather, we can call it an addition instead of a variation. Variation number 1, where we had this form, b times a to the power of x, where we included that b there, and we looked at its effect on the graph. And we noted on the previous video that what that does on the original, so if this is the original, then what that variation does is that it changes that y-intercept where the x stays the same and the y-intercept is b. Okay, and we've also noted that the asymptote, the horizontal asymptote, stays the same for the variation. Okay, so b is the b in the equation, b times a to the power of x. Okay, so all of this was covered in a previous video. Okay, so just to add on to that previous video, before I move on to the other variations, I'm just gonna explain something further regarding b. Okay, so let's just adding on to the previous video. So if this is your form, right, your variation number 1 times b times a to the power of x. I only in the previous video explained the situation where b is greater than 0. Okay, so in other words, this was where b is positive. B was positive. Okay, b was positive. But just to clarify something, b does not necessarily have to be positive, even though my examples in the previous video were positive b's. The same thing applies with if b is negative, but I want you to note the following. Let's say I've got, let's just write that down, just to write what we're doing. Let's just write it down as a question. What if b is negative, right? What if b is negative? Question mark. If I've got my Cartesian plane there, and I've got my original graph. My original graph, you and I know, looks like that. Okay, that's my original graph, and we know that that there is your y-intercept. That's 0 and b. Okay, we know that that's b there. And in this case, for our original form, we know that the original form of our equation is y is equal to a to the power of x. And you will agree with me that the number that comes before the a to the power of x is 1, right? So that's 1 there. That's 1 times a to the power of x. So for our original form, b is equal to 1, right? B is equal to 1 for original form. So in that case, that's going to be 1 for original form. And we know from a previous video that whatever the value of b is, we know that whatever the value for b is, that's the value that we're going to get there. That's our y-intercept. Okay, that is going to be our y-intercept. So what if b is negative? Okay, let's address the main question now. What if b is negative? Well, let's go to the next slide for that and show you. So I need a bit of space, so let's take it up on the next slide. So if b is negative, I've got my Cartesian plane, got my Cartesian plane, got my Cartesian plane, got my Cartesian plane, got my original graph, and then I've got 0 and b. Okay, so if b is negative, by the logic that I just put forward to you, that b is the y-intercept of our exponential function. If b is negative, right? If b is negative, then you will agree with me. Let's say I've got y is equal to 2 to the power of 2x. You will agree with me that in this case b is equal to 2, and therefore the y-intercept there is 0 and 2. You will agree with me. Now, what if instead of this equation, y is equal to 2 times 2 to the power of x, what if I've got y, let me just write it here, add it on here. Let's say that's negative. Actually, let me use a different color. What if that's negative? What if I've got y is equal to minus 2 times 2 to the power of x? Well, by the logic that I put forward to you from the previous video and the beginning of this video, if that is your y-intercept, then you will agree with me that my graph will pass through minus 2 here. Okay, my graph will pass through minus 2 here. Now, you will remember from the previous video that I said b, the only thing that b affects, right, the only thing that the b affects is the y-intercept from the two main characteristics that I showed you from the first video. Remember what the two main characteristics are. The two main characteristics are the y-intercept and the asymptote, okay, of the exponential. It's the y-intercept. Remember, it's the y-intercept and the asymptote. And I did say in the previous video that b changes the y-intercept, but it doesn't change the asymptote of the original form or of the original graph. The asymptote stays at y is equal to 0, so that doesn't change, but the y-intercept changes. So you will agree with me that for this form here, for this equation here, the y-intercept will be minus 2. Okay, it will be minus 2, but what does the negative do? Well, this is why this is what I'm explaining here now, why I wanted to point out the asymptote. Now, if the intercept is minus 2, right, the y-intercept is minus 2, and the asymptote still stays the same. The asymptote is still there. The asymptote is still on your x-axis, so your graph still doesn't touch your x-axis. It still doesn't touch your x-axis. Then how will this graph look? Well, this graph has to keep the same behavior. What do I mean by the same behavior? Well, moving towards the left, it's got to approach your asymptote just like it did up here, right? It's got to approach your asymptote moving to the left, and moving to the right, it's got to move away from your asymptote. It's got to move away from your asymptote, and it's got to move away at an accelerated rate, right? So what will our graph look like? Well, my graph will look like, just try to draw it nicely. My graph will look like that. Okay, my graph will look like that. This is what my graph will look like. So the negative, notice what the negative does. The negative only reflects. It reflects your graph about the x-axis, about this axis here, the x-axis. It reflects your graph about the x-axis. So if you look at this graph down here, this is a reflection of this graph up here. Okay, so that's all that it does. So your behavior of B still does the exact same thing that we said it does in the previous video, but if it's negative, then it still behaves the exact same way that we said it behaves in the previous video, except that it's a reflection of what you would have had in the on the other side of the x-axis. Okay, let's give you another example. Say if you've got let me just draw in Cartesian plane. I like saying remember to label your Cartesian plane. Okay, so if you've got, let's say, y is equal to minus 3 to the power of x, and I'll ask you to sketch this. Well, if you know what the original form looks like, right? The original form we know looks like that. Okay, we know the original form looks like that. Okay, and we know that that value there is not negative 3. As a matter of fact, that value is minus 1 times 3 to the power of x. That's what this equation is actually looks like. Now, how do I know this? Why am I saying it's minus 1 times 3 to the power of x? Remember, in the very first video of our lessons on the exponential functions, I said to you a is greater than 1. Okay, so we're only covering exponential functions for the situation where a is greater than 1. Okay, a cannot be greater than 1. In this case, a is equal to 3. A is not equal to negative 3. The negative is negative 1 there. It's the negative 1 that you multiply by the 3 to the power of x. Okay, so that's what you have here. So how would this graph look if you had to sketch it? Well, you know that if it's negative 1 times 3 to the power of x, you know that your graph will pass through negative 3 there, right? It'll pass through negative 3 because it's a reflection of 3. So if that was 3 there, okay, if that was 3 there, if that was 3 there, then this new graph would be a reflection of that, and it would look like that. Okay, where your y-intercept is 0 and minus 3. Okay, so you treat it exactly the same way as I said you must treat it in a previous video, except that you plot it on the negative side and you keep the asymptote where it is on the x-axis, and you make your graph approach the asymptote when it's moving to the left, and it's moving away from the asymptote when it's moving to the right, but then your y-intercept happens to be on the negative side because of that negative sign there. Okay, so let's do 2 more examples. I'm going to do them quickly because I think I've already explained in principle what happens, and I think should be easily understandable by now. So if I've got y is equal to minus 5 times 2 to the power of x, well, you know that this graph will look like this, where your y-intercept is 0 and negative 5. Okay, 0 and negative 5. As a matter of fact, I think I made an error in the previous thing. This is not going to be 3. Sorry, this is going to actually be 1. This is going to be 1, and this is going to be minus 1. Okay, why is it going to be minus 1? Okay, so I made an error. In that case. Remember, b is negative 1. B is negative 1. So your y-intercept will be negative 1 there. Okay, it will be negative 1. Remember what b is. B tells you your y-intercept. B tells you your y-intercept. Okay, I shouldn't have made that mistake. I hope you guys caught it when I made it, and I hope you were screaming at the video that it can't be. Okay, so your intercept there in that case is 1, and your intercept in this case is negative 1. Why? Because b tells you your value of your y-intercept. Okay, b tells you the value of your y-intercept. So in this case, your y-intercept b is 5. B is minus 5. Okay, so b is negative 5. Let's see on the previous things. See here, b is negative 2, so that's right. And then and then yeah, so I even wrote it here, b it would be 2 if it was positive. Okay, so this is fine, this is fine. All right, so let's do 2 more examples. Sorry for that mistake. Let's do 2 more examples. If you've got that there, and then I've got y is equal to minus 6 times 100 to the power of x, right? Then my graph would look like this, where your y-intercept is at minus 6. Okay, your y-intercept is at minus 6. If I had y is equal to minus 6 to the power of x, then your y-intercept, your graph would look like there. It would be at the bottom there, and then your y-intercept there would be 0 and -1. Okay, because the -1 there, you have a -1 there, and then the 6 is with the exponent of x. Okay, so I hope that makes sense. I hope that's not confusing. Okay, so now let's focus on the second variation. Now that we've addressed that, let's focus on the second variation of the exponential function. The second variation that I want us to look at, okay, the second variation is as follows. It is y is equal to a to the power of x, and then I'm going to say plus b. Okay, a to the power of x plus b. So the second variation, or as a matter of fact, let me not call it b, let me call it c, because I called that first variation b. Let me call this one c. It doesn't really matter what you call it, it's just you have a variable, you're adding a variable to your original form. So you will agree with me that this is your original form. This is what I've been referring to as the original form, right? That black part of the equation is the original, and the blue part is the addition or the variation to the original form. So what's going to happen if we have an equation in this form? Well, let's find out. Say you've got a table. Okay, you've got a table, and in this table you've got y is equal to a to the power of x. Okay, and then here you've got y is equal to a to the power of x plus c. Okay, let's give numbers to that. Okay, so let's say your y is equal to 2 to the power of x, and in this case let's say y is equal to 2 to the power of x. Let me write out my x nicely. To the power of x plus 1. Okay, and then we split this into 2 more columns. Then I've got x here and I've got y here. I've got x here and I've got y here. Now I just use random values. I like using -1, 0, 0, 1, 2. Maybe we'll also use 3. Okay, -1, 0, 1, 2. Let's use 3. Now what's going to happen? Okay, let's see what values of y are we going to get for this equation, and let's see what values of y are we going to get for this equation, and let's compare them just like we did when we looked at the first variation. Okay, so let's start with this one. When just change color of my pen. When x is equal to -1, right? For this one, when x is equal to -1, y is equal to 2 to the power of -1, which is 0.5. Okay, that's 0.5. Right, for the second, for this second equation here on this table, when x is equal to -1, 2 to the power of -1 plus 1, y is equal to that. So that's half plus 1. So that's going to give you 1.5, 1.5. Okay, So when x is equal to 0, y is equal to 2 to the power of 0, and that is going to give you y. Right? When x is equal to 0 for this second equation, you're going to get 2 to the power of 0 plus 1, and that's going to give you 2. Right? That's going to be 1 plus 1, which is going to give you 2. Okay, so when x is equal to 1, this is going to give you 2 to the power of 1, which is 2. When x is equal to 1, in this case, that's going to give you 2 to the power of 1 plus 1. It's going to give you 3. In this case, when x is equal to 2, y is equal to 2 to the power of 2, and that's going to give you 4. And then in this case, 2 to the power of 2 plus 1, that's going to give you 5. In this case, when x is equal to 3, that's going to be 2 to the power of 3. That's going to be 2 times 2 times 2. It's going to be 8. And in this case, that's going to give you 2 to the power of 3 plus 1. It's going to be 8 plus 1. It's going to be 9. It's going to be 9. Now, notice what the difference is. Notice what the difference is between these groups of y values. When y, for the first equation, when y is 0.5, for the second equation, y is 1.5. Okay, so that's just, it's bigger. Let's look at what happens for these two. When this one is 1, this one is 2. When this one is 2, this one is 3. When this one is 4, this one is 5. When this one is 8, this one is 9. So you will notice that for this equation here, all the y values are bigger by 1 unit. Okay, by just one unit. So when this is 0.5, 0.5 plus 1 is equal to 1.5. That's 1 unit. When this one is 1, 1 plus 1 is 2. That's 1 unit. When this one is 2, 2 plus 1 is 3. That's 1 unit. When this one is 4, 4 plus 1 is 5. That's 1 unit. And so on and so forth, right? When this one is 8, 8 plus 1 is 9, and that's 1 unit. Okay, so where does this 1 unit come from? Well, it's that 1 unit that we have there, right? And what does this 1 unit mean? Well, let's show it on a graph. Let's show it. Remember, we're adding the 1 unit to all the y values of the graphs, right? So let's just plot that out there. So we've got our Cartesian plane there. We've got our Cartesian plane there. We've got our original graph that looks like that. And we know that the equation of this graph is y is equal to 2 to the power of x. Okay, let me just write it out a bit neater. Y is equal to 2 to the power of x. Okay, we know that that's the equation for that graph. And we know that the second equation is y is equal to 2 to the power of x plus 1. And we know that that plus 1 there, this plus 1 there, is simply saying to us, you're going to take the original equation, right? You're going to take this original equation, and you're going to add 1 unit to each of the values that you get for your original, right? So we know what our original looks like. Our original, we sketched it out here. This is what our original looks like, right? We're going to take that original and we're going to move it up. All the points that make up your original graph, we're going to move them up by 1 unit. All of them we're going to move up by 1 unit. All of them. Now, when I say all of them, I'm including the y-intercept. I'm including the y-intercept, and I'm including the asymptote. Okay, I'm including the y-intercept and I'm including the asymptote. Now you will remember that when we were changing b, right? When I was explaining b earlier on in this video, and in the previous video, I said to you that y is equal to b times a to the power of x. I said that this gives you your y-intercept, right? That's what I said. I said it's a scaling factor. It scales your graph up by a factor of b, right? And that b value is the value that you're going to have there as your y value for your y-intercept, or as your y value. okay, right on your y-axis. So now what I'm saying to you is that, okay, now we've got this new form. Now in this new form here, we've got y is equal to a to the power of x plus c. And I'm saying to you, the c value tells you how much to shift your graph vertically, right? Whether it's upwards or it's downwards. If it's negative, you're going to move your graph downwards. If it's positive, you're going to move your graph upwards. All the points on your graph. Now, not just the points on your graph. You're not just going to move the points on your graph, but you're going to move your asymptote as well. Okay, you're going to move your asymptote as well. So now let's do that. Okay, let's do that. Let's actually do that here, right here on this sheet. Okay, so I'm going to do that. I'm going to remove you. Okay, and I'm going to sketch this new graph. So I'm going to sketch the graph with this equation here. So what happens from our previous table, you noticed that we move all the points on our graph by 1 unit upwards, and we also move our asymptote by 1 unit upwards. Okay, so let us do that quickly. Okay, so if we move this by 1 unit, let's say those are our units there. Or let's do this. Let's say this is the original, the graph that I sketched is the original, and we know that there, we actually write it in black ink. We know that this is the original. We know that this is given by 2 to the power of x, right? This is given by 2 to the power of x. Therefore, we know that the asymptote there, the y-intercept there is 1. How do I know that it's 1? Well, because the value of b here is 1. B in this case is equal to 1. Okay, remember, just in case you've forgotten, if I've got y is equal to 2 to the power of x, the value that has x as an exponent is not your b. Your b is on its own. It doesn't have an exponent of x next to it. So if you were to expand this, you would have 1 times 2 to the power of x. Therefore, your b is 1. And that is why your y value there is 1. Okay, so just please remember that. That's very important to understand. That's very important to remember. So this is why your y-intercept in that case is 0 and 1. Right, now what about this one here? What about this graph at the bottom there? We move it up by 1 unit, including the asymptote. So the asymptote we know lies on the x-axis. There's your asymptote there, but we want to move it up by 1 unit. Well, you've got your 1 there, right? This is where your 1 is. So your asymptote will be, by the way, your asymptote, you can draw it as a dashed line. That's how they usually draw it, as a dashed line. So your asymptote will be there, right? That's where your new asymptote will be, right? That's your asymptote. ASY for asymptote. Okay, and your graph, whereas before it had 1 as your y-intercept, the original graph would have had y as your intercept. The original part of this equation has your y-intercept as 0 and 1. Your new part, every y value, you add 1 onto it. So that one is going to be, you're just going to say that 1 plus 1 is going to give you a 2. So it'll be somewhere there. And then that's going to be your new intercept, just the y value. The x value stays the same. Your y value is there, and that's your new y-intercept and your new graph. Now, since this is your new asymptote in blue here, since this is your new asymptote, your graph is not going to touch that. It's going to approach that line, but it's not going to touch it. So your graph is going to, try to draw it nicely. Your graph is going to pass through your y-intercept. It's going to approach the blue line, but it's never going to touch it. It's never going to touch it. Okay, and your graph is going to look like that. Okay, so all that happened is that this black line moved up by 1 unit. This black line moved up by 1 unit, but not only did the black line move up by 1 unit, but the asymptote moved up by 1 unit as well. Okay, asymptote moved up by 1 unit as well. Okay, so let me sort of summarize that before I give more examples. So if you've got y is equal to a to the power of x plus c. Now what this means is that you've got your original graph, what I call your original graph, shifting up or down depending on the sign there by C units. Your original graph will look like that. This is why it's so important to understand your original graph, the behavior of your original graph and how it works. And you will know that there is 0 and 1 on your original graph. Or you can even say, because now that we've covered that first variation, 0 and b, right? 0 and b, whatever the value of b is there. Now, as soon as you add c, what's going to happen is that you are going to say this graph, that b there is going to be b plus c, right? And that's going to be your new y-intercept. Either your graph is going to move up if c is positive, right? If c is positive, or it's going to move, let's just do an arrow, or it's going to move down if c is negative, right? And it's going to move down. Now, remember, you will see that when I say move down, now my graph cuts through the x-axis. That doesn't matter, because if the graph moves down, the graph moves up or down with the asymptote. So if it moves down, then your asymptote will have moved down as well. Okay, so let's do a couple of examples to illustrate that so that it makes sense. If I say to you, sketch the graph y is equal to, I've been using 2, let me use 4 to the power of x minus 2. Well, first thing you do is you will draw your Cartesian plane. And then you will look at your graph and you will say, okay, what is the original portion of this graph? Well, the original portion of this graph is that. If I had to express this graph in terms of its original equation, I would have y is equal to 4 to the power of x, right? But what happens to my original graph? Well, firstly, let me sketch it. You don't need to sketch it. I'm only sketching it because I'm explaining, right? You don't need to sketch the original. The original would look like that, right? That's what the original would look like. And the original would have an intercept of 0 and 1 there. Okay, cool. Now that I know what my original will look like, what does this graph that I'm being asked to sketch look like? Well, I know that it shifts down by 2 units. So I'm going to take this graph here and I'm going to move it down by 2 units. That's essentially what this thing is telling me, right? Shift the original graph of 4 to the power of x down by 2 units. Not just the graph itself, but also the asymptote. We know that the asymptote, the original asymptote is there, so I want to shift it down by 2 units. So let's start with the asymptote. So if the asymptote is there originally, then I'm going to say 1, 2. Then that's going to be minus 2, right? So this is where my asymptote is going to be. My asymptote is going to be there at minus 2. So this is the line that my graph will not touch. This is the line that my graph will always be approaching but not touch. Okay, now I have to take this y value here and shift it down by 2 units as well. So that's going to be 1, because that's the y value there, minus 2 units, which is that value there. What is 1 minus 2? 1 minus 2 is equal to, just erase that, it's equal to minus 1, which is that point there. And then my new graph will look like that. Okay, my new graph will look like that. It will pass through that point there, and it will always be approaching but never reach that horizontal asymptote there. And that's what my new graph will look like. Okay, let's do 2 more examples quickly. So I've got that. That's my thing there. And I say y is equal to 2 to the power of, let's just say 2 times 3, right, to the power of x minus 1. Okay, so that's 2 times 3 to the power of x minus 1. And I say sketch this graph quickly. Well, you will see that you will tell me that, comma, that value of b there, b is equal to 2, and c is equal to negative 1. B is equal to 2 and C is equal to negative 1. Okay, let me actually B is equal to 2 and c is equal to -1. Now you will tell me that, okay, so my original graph, the original graph would have been that portion there, 3 to the power of x. That would have been my original graph, right? It would have been 3 to the power of x, right? And 3 to the power of x, if I should sketch it, would pass through there somewhere, would do that, and that there would be 0 and 1. Okay, now you will tell me that now, but b is 2, right? B is 2, so that can't be 1 there. It should be 2 for your first variation, or for your first addition, right? So that's going to be 2. Okay, and then now that you've taken care of that part of the equation, now you will tell me, but no, it can't be 2 because there's that -1 there. There's that -1 there. So we must, from that 2, subtract 1, right? From that 2, we must subtract 1. And how much are we left with? Well, we are left with 1. So we then come back to 1 again. See how you're working towards the final product by changing things. Okay, then you get back to 1 again. And then, so this will be your final y-intercept. Now we're done with the y-intercept. What about your asymptote? What about your asymptote? Well, your asymptote also shifts. Remember, this here not only moves just the graph, but it also moves the asymptote. It moves the asymptote as well, right? So your asymptote will move from, if you had the original is 3 to the power of x. That's the original. You know that the asymptote is there. Okay, the asymptote is there, but then that -1 there tells you to shift your asymptote downwards by 1 unit. So your asymptote will go down by 1 unit there. So your asymptote will be there. So your graph, your final graph will look as follows. Your final graph will look as follows. Let me just erase these things, add them back. So that's that, erase that. Okay, let me just leave those weird portions. So your asymptote will be here. It will be there. Your asymptote will be there at -1, and your graph, remember, will still pass through. We worked our way back and forth. Your graph will still pass through there. That's 1 there. Okay, your y value is 1, so the coordinates are 0 and 1, but your asymptote will have shifted down by 1 unit because of that 1 there. And then your final graph will look, it'll pass through there. It'll always be approaching your asymptote but never reach it, and then it will continue on up there and it'll look like that. Okay, so that is what your graph will look like, and that is how you would basically sketch this this graph here. Okay, so let's do another quick one. Say you've got y is equal to 4 times 2. I've been using 2. 4 times 4 to the power of x. As a matter of fact, let me say -4 times 4 to the power of x minus 6. Okay, minus 6. Now let us work our way through. Let's work our way through this problem. Firstly, you will tell me that, okay, the original part of this equation, the original part is that, right? It's 4 to the power of x. Now, if I had to sketch 4 to the power of x, what would it look like? It would look like that, right? I know that my asymptote is on my x-axis, and I know that my y-intercept is 0 and 1. This is for the original part, just for the original part, just for this part there. Okay, I'm going to keep the original in black. Now you're going to tell me, okay, let me just take that 4 out, that -4 out there, and write it in blue. so that we can properly identify what's what. So that's minus 4. Okay, that's minus 4. And then the negative 6 there, I'm going to write in red so that we can follow. Okay, so now you will tell me that, okay, so the black is the original. That's the original. That's what we have in black, right? Now, let's focus on the blue. Now, the blue here, you will tell me that B is equal to minus 4. So you will tell me that, okay, firstly, I have to take it up to 4, right? If that's 1, let's say that's 2, that's 3, that's 4. That's 4 there. I have to take it up to 4, and then I have to reflect it about the x-axis, right? So that's going to be 1, 2, 3, 4. So my graph will have to pass through there. Okay, it'll have to pass through there. For the blue, right? For the blue. Now, I say for the blue, my graph looks like that. Let me just... For the blue, my graph looks like that. Okay, it looks like that. That's what my graph looks like in the blue. Okay, so now I've dealt with the blue. Fine, I'm done with the blue. Now I'm going to say, okay, cool. Now I'm going to deal with the red. I'm going to deal with the red. Now with the red, I would have had to take my original graph, right, and move it down by 6 units. Right, I would have had to take my original graph and move it down by 6 units. Okay, but in this case, what happened is that I've got this graph. I have to take this graph now, which is the graph that I've plotted here. This is the graph that I've plotted here, right? Let me just make a blue square so that I show you this graph here. This entire graph here is this graph that you see here. So what I have to do now is take the asymptote of this graph and move it down by 6 units, right? Take that asymptote and move it down by 6 units. But I'm not only just moving the graph down, I'm moving the entire asymptote down with the graph. Okay, so the graph and the asymptote. So the asymptote for this graph, you will agree with me, the asymptote for this graph is there. Because remember, this graph only considered B, the influence of B, and B is minus 4. That graph only considered the influence of minus B. Now, for us to consider the influence of minus 6, we have to take that asymptote and move it down by 6 units. So the asymptote then is at minus 6. So that's 4, that's 5, that's 6. Minus 6 is down there. So the asymptote would be here at minus 6. So what's going to happen? This entire graph will move down by 6 units. It'll move down by 6 units so that it approaches your new asymptote, but it doesn't touch it. Okay, I don't have space now. So your graph and then your intercept at that point there would be minus 4 minus 6, which is minus 10. Okay, so let me sketch this on a new page so that we can see everything nice and clearly. See how you work your way, you work your way to the final product using bits and pieces of the graph, you know. So you've got, so your final graph, your final graph, your final graph will look like that. Okay, where your y-intercept is 0 and minus 10, and your asymptote is at minus 6, and the equation is y is equal to negative 4 times 4 to the power of x minus 6. Okay, and then this is what your graph would look like. You'll see that we've combined the influence of B and we've combined the influence of C. Okay, so C moves the entire graph with the asymptote by C units, okay, vertically. And then B only scales your graph. It scales your graph. So you work your way from left to right of the equation that you're given. Okay, firstly you include the influence of B, then you include the influence of C, then you'll get your final product. Okay, so a bit of practice, more practice with this should make it quite easy to understand and to implement. but this is the influence. These are the influences of B and C on your graph. Okay, so on the next video, we will focus on the influence on the next variation, the final variation for your exponential function before we move on to something else. Okay, so hope this makes sense, and let's meet again on the next video. Till next time. Lesson number one, lesson number one. Lesson number one, lesson number one.